And good morning and good evening, everyone. And thank you for taking the time to join in on this session, especially to those of you that have already been on here for more than 8 hours now. Also, a very big thank you to Fluidtech and the sponsors who organized and made this summit possible. I've already listened in on a couple great sessions, and I look forward to viewing the rest of them later. But I'm rather happy that the sessions can be watched outside of the time frame of the summit, because it was a very difficult choice between staying up all night or getting some sleep in order to deliver an understandable talk to you all. And today I want to give you a brief overview of the Solar Turbines digital solutions platform, how we use it to improve equipment reliability, and how we're leveraging this platform to monitor lube oil condition and health. Before that, just a very quick background on myself. As Greg mentioned, I'm currently with Solar Turbines, and I have been for the past 9 years in the technical services team as a product support manager and lube oil support team lead. Prior to getting into technical services, I was also a marine certification engineer in my first few years at Solar. And prior to joining Solar, I was an air quality engineer with environmental consulting and technology. My educational background is thoroughly in chemical engineering, both my bachelor's and master's degrees. And in part, that is why the lube oil topic is so fascinating to me, and it hits fairly close to home. Now, I'm hoping that some or most of you have heard of Solar Turbines by now. We manufacture industrial gas turbines, primarily for oil and gas and power generation applications in the size range between 1 to 23 megawatts. We started manufacturing turbines in the 1960s. However, the Solar history spans almost an entire century. We started out as an airplane manufacturer here in San Diego, and we actually provided some of the parts for the Spirit of St. Louis airplane when it was assembled. And for those of you that are wondering why the name Solar Turbines, initially the name of the company at the time of the founding was the Pruden San Diego Airplane Company. It later became the Solar Aircraft Company in 1929. The name was then changed to Solar Turbines Incorporated in 1960 when we started manufacturing turbines. However, the word solar itself was a tribute to the San Diego sunshine, of which we honestly have plenty, and sometimes I would gladly trade for a little bit of rain if we get a chance. So just a quick overview of the range of turbines and compressors manufactured by Solar. On the left side, you'll see the range of turbines, and on the right side, there's a range of the compressor configurations. However, this photo doesn't do justice to the rest of the package that goes with this equipment. It contains a skid, which is also a lube oil tank, and all the supporting equipment that make these turbines and compressors run. And we, since our start in 1960, we have sold about 15,000 turbines and 6,000 compressors since we started manufacturing them. And it's actually amazing that some of those first units that we produced are still out in operation and in the field. The turbines, they drive compressors, pumps, and generators mainly, with the Titan 250 being the largest and the newest turbine, providing 30,000 horsepower. Now, as every manufacturer of large industrial equipment knows, the monitoring, the troubleshooting, the data collection, the sharing can be a challenge even in the best of scenarios. But even more so in remote locations, for example, gas pipeline compressor stations, which typically tend to be out in very remote areas, or even offshore platforms. We know that nothing really replaces having the boots on the ground or an expert's eyes and hands on the machine. However, there is an undeniable value in remote, live, and continuous monitoring of the equipment. Just like us, with people, in a few very short years, we went from the rotary phone to the incredible level of connectivity and technology that we currently have on our hands. Similarly, the connectivity for machinery and equipment has rapidly become the new norm in industry. Because I'm sure some of our Solar Digital team members are listening in, I will apologize for changing their catchphrase above. However, as recent events have shown us very clearly, the digital demand is already here. These times of the globally restricted travel, restricted site access, they only emphasize further the value of remote and real-time equipment monitoring. And I have the feeling that they will agree with me because while the in-site connectivity was a customer option previously, going forward, the connectivity will be a standard for all new units because we truly do see the value in getting the data. For solar, the digital solutions platform didn't only dovetail equipment monitoring and troubleshooting really wonderfully with the on-site presence, but it has brought together a lot of aspects of support that historically would operate independently of one another, such as training, parts management, repair and overhaul, just to name a few. Another major benefit of centralizing site and equipment information into one database is that not only are we capable of reviewing historical data for specific units going back a long time, but we can also use that entire data set to come up with predictive analytics to assess how a particular unit performs in comparison to the rest of the connected fleet, for example. And thus be able to drive proactive actions in order to prevent downtime for the customer, which is ultimately the main goal. And now, just to give you a real view of the Insight platform, with the asterisk being that what we see here is really just a sliver of the monitored and calculated parameters from the diagnostic tool. It is the same capability that our solar team and the customers have available at our fingertips to assess how a particular unit is doing at any point in time. So in the charts above, it depicts how various parameters trend over time. So for example, up here in the upper left corner, the lube header pressure, one of the things that it can tell us is to assess whether the bearings are getting adequate lubrication at all times, for example. Or in the upper right corner, the bearing vibration, it can capture small changing trends much earlier than before we reach the actual limit. Many of these parameters are direct inputs from sensors on the turbine and on the package. However, the algorithm also calculates many of the charted parameters from measured data, providing a much broader analysis of the equipment operation and health than what we can measure directly on the equipment. So in terms of the trends themselves, everything on this particular unit looks stable and not very exciting. However, in the world of turbine monitoring, we do like things to not be very exciting. And so the one parameter charts that I just showed, they're great for a quick overview. But when we need a deeper dive, it is paramount to bring all this data together into one place. And the snapshot that you see currently on the screen, this is from our Trendo tool. It only shows, again, a very small section of the engine and package parameters that are available for review. Otherwise, I have the feeling the chart would probably look more like a Jason Pollock art piece if we included all the parameters on there. But it is representative of how we use the tool as well. We focus on specific parameters and how they trend in relation to one another at different operating points. The same thing applies to the time scale and to the data granularity. So we are able to zoom out and review long-term trends, for example, or zoom in on a particular event of interest to review the equipment behavior down to a single second. And Trendo is probably the tool that myself and all the team members in our tech services group keep open on our computer at all times. And we use heavily for troubleshooting remotely, but also for collaborating with our field teams. Because as they say, a picture is worth 1,000 words, but sharing a real-time trending tool for monitoring complicated machinery has got to be worth at least a little more than that. And now before I get into how we are leveraging all of these Insight platform capabilities to monitor oil conditioning and health, just a quick overview of the typical oil monitoring approach that has been historically employed and is still in large part the main tool that we have. So an oil sample is periodically extracted from the tank or other siphoning port on the unit. It is sent to a lab for analysis of specific parameters, and a report similar to the one that you see currently on the screen is generated. And then a customer or someone like myself will read the report and assess these parameters against the established acceptable limits to deem whether the oil is generally healthy or not. And what we have facilitated recently through an application programming interface or an API, we're able to connect labs directly to our database and digitally transmit all of that analysis data into Insight. So then the algorithm takes the data, it sorts it into buckets, quote unquote, pertaining to specific units, and therefore it creates a historical library from all the oil sample analysis on that particular unit. So this is paramount because as important as knowing the condition of the oil at a specific point in time is, it is more informative to look for upward or downward trends over multiple samples. For example, in the snapshot that we have on the screen right now, the Carl Fisher water content reported for this particular sample was tested at 122 ppm, which is well within the acceptable limits based on the specification and not an unusual level of water to see, especially on specific oil formulations or particular sites. However, if the trend over multiple samples shows that over time the water content has increased from one sample to the next, it is alerting us of a potential ongoing water ingress situation that needs to be investigated and addressed immediately before it becomes worse. Therefore, as mentioned in the slide, in order to use oil analysis more as a predictive and a proactive tool instead of simply a reactive approach, the trend is your best friend. And when we first started collaborating with a digital team in order to include visual trending of the oil analysis results into the Insight platform, we first focused on some of the highest criticality parameters, such as the oil viscosity. And while we can all agree on this forum that all aspects of oil analysis are critical, and that is why we test for them regularly, in the operation of a gas turbine, a drastic change in viscosity can be catastrophic. And one example is, for example, the alteration of the oil film thickness between the bearing and the shaft, where the oil film gets either too thin or too thick for proper operation. So our lube oil specification mandates a fairly narrow range of acceptable viscosity fluctuation, but being able to notice viscosity increases or decreases prior to crossing those boundaries is pretty important in preventing a potential failure in the future. And not by coincidence, the water content was also one of the first parameters that we started trending on Insight, because aside from being a very good catalyst for oxidation reactions and varnish formation and the potential for rust formation, for example, the immediate effect of a severe water contamination is a rapid increase or a rapid change in the viscosity of the oil. In cases when glycol has been present in the oil as well, we have also observed the contamination to have both effects. So first decreasing and then rapidly increasing the viscosity of the oil, both of which are highly undesirable scenarios. Thankfully, in the world of gas turbines, a severe water ingress scenario is generally rare. However, they do happen, and when they do, they result in serious damage to the equipment, as well as an extensive downtime and cost for the thorough system cleanup. Therefore, we deem it very important to catch these situations very early on in order to take immediate action to address the water source and, if needed, to replace the contaminated oil. Particle count, on the other hand, or oil cleanliness, was another important aspect for us to start trending early on. And in our specification, we provide strict limits for the acceptable cleanliness level of both new and in-service oils. And we use a trending capability in conjunction with other sensor data collected from the system in order to trigger certain inspections or maintenance actions. For example, the delta pressure across the lube oil filter, it can reveal whether the filter is clean, starting to get clogged, or other problems. When events of high delta pressure across the filter become more frequent, we have an indication of contamination, possibly, and the results from a high particle count test can confirm the contamination. Or when these results are low, they can point us in a different direction to look at potential issues such as filter damage, for example. And the total acid number, or TAN, was also a parameter that we decided to add to the trending capability early on. And I wanted to point out that here we have an example of when things do get exciting. If you look closely at the chart, you will notice that the TAN started to increase over time, which is a good indication that the rate of oil oxidation is speeding up in this particular unit. So in early 2018, we see that an oil sample was sent out for analysis right before a several-month period of inoperation. And we see the TAN value being analyzed at 0.8. So therefore, it's fairly high. What is even more telling, however, is that after several months of inactivity, the next oil sample analysis reveals an acid number that is much higher. We are in above 1.5 at this point, which indicates that the oxidation reactions continued to take place even while the oil was at rest and at quite a rapid pace. So in this particular case, the oil was completely drained and replaced on the unit. And we can see in the most recent sample points, all looks good, and we are back to having boring and non-exciting data. Now, I know you might ask why TAN and not NPC or RPVOT in order to assess the oil degradation. And one reason is because both of these tests, the NPC and the RPVOT, are fairly new. They have not become a standard for all labs yet, especially on certain international locations. And therefore, they're not always available. And as a consequence, these tests are also fairly rare in historical lube oil test data. So we wanted to make the most of the data that we already had available, and TAN is commonly reported in a lot of lube oil analysis. However, both NPC and RPVOT trending are currently in work, and we expect to add that capability shortly for a fuller picture of the oil condition. So what is next, and where do we go from here? And our goal is to take the data integration even further, to incorporate the oil analysis data with other turbine and package monitor parameters in order to get that complete pictures like we see earlier in the Trendo, where various parameters are trended against one another to assess how behavior and correlation changes. And we want to have the same correlation between lube oil analysis results and equipment parameters. So for example, does an upward trend in oil oxidation parameters correlate to an existing or an increasing trend in bearing vibration? What lessons can we learn from analysis data from the entire connected fleet? Do some oils show better resistance to oxidation and deposit formation under certain conditions or in particular applications? And how early can we realistically and reliably predict machinery wear by using elemental analysis trending? All of these are questions that we have started to explore with the help of these digital tools, but we look forward to what else we can learn going forward. And with that, I would like to thank you all for your time, and I look forward to the discussions in the Q&A section. Thank you.